All right, so we're talking about growth and decay. All right, so I.1 is specifically about exponential growth, and then I.2 is specifically about exponential decay. So consider a population of mice described by the equation P of t equals 2 times 1.15 to the power of t, where t is the time in months. Part A. What is the initial population of mice? So, if we want the initial population of mice, we're asked, how many mice are there when time is 0? That's how many mice there are going to be initially, right? And so we have 2 times 1.15 to the power of 0. Okay, 2 times 1.15 to the power of 0, that's going to be 2 times 1, it's going to be 2. Initially, in this zone that we're investigating or modelling, there are 2 mice. Okay, part B, how many mice are there after 5 months? Okay, so now they're saying T is 5. So that means we're finding P of 5. How many mice are there after 5 months? So we're going to put the 5 put that one in our calculator. .02, which is 4 mice. Okay. The next one. How long will it take for the population to reach 60 mice? So now we're saying, how long will it take for this equation, 2 times 1.15 to the power of t, to equal 60? That's the equation we're trying to solve for t. So there are 2 strategies we can use to solve this, right? One of them is using the graph, which is probably the one I want us to do, following on from H, and then the other one would be using equation solver, which is probably faster, but I'm reluctant to use it because it doesn't follow on from the skill we just developed. So what we're going to do is we're going to graph this equation. We're going to graph the function for the mice. All right, so we'll go back to our graph menu, and we're going to type in 2 times 1.15 to the power of x. All right, 2 times 1.15 to the power of x. We use x and t interchangeably, so be comfortable with that. They just mean variable, right? Now, what is, so we've got the graph there, let's talk about the V window. So Shift F3 to bring up the V window. And for our X min, X max, Y min, Y max. Now for these values, okay, it doesn't, when we're talking about time, we never consider negative values of time. We only consider positive values of time. The model only makes sense in the positive context of time. So our X min, our minimum value of time, is 0. That's when we start investigating the population. Of course, otherwise it's not going to make sense, because otherwise we're going to have 0.4 mice. Okay? So we only consider from time is 0. X max, we're not too sure what we should put here yet. All right, so for now, let's just put 10, and we can adjust it accordingly. The X max, how far into the future are we going to anticipate? For our Y min, the lowest the population could possibly be is if it all decayed, 0. We can't have a negative population. That doesn't make sense in the context of the problem. And then Y max, well, we're interested in when the population reaches 60 mice. So let's just set the Y max as something just slightly above that. Let's go for 70. So I'll bring up my window, I'll do that. 0 to 10, and 0 to 70. Okay. Now, what's going on here, when I've sketched it, is it looks like that. So I need to crank my X out a fair bit more, because I want to know, right, at the moment, 60's up here. All right, and so like the most it gets to, let's see, when x is 10, the highest it gets to is 8. So I need to crank the x max out a bit more. So we'll go back to our V window. This is the troubleshooting, right? Let's double it. For our x max, change it to 20. Okay, we're starting to get there. It's still not enough. So V window, crank it to 30. And there I think we've reached it now when I set my x max to 30. Okay, now I can go gsolve, x count. I want to know the x value when y is 60. When y is 60, x equals 24.33. Okay, so what have we answered there? We've said it takes 24.33 months for these 2 mice to reach a population of 60 mice. Okay, it's undergoing exponential growth. So just over 2 years. All right, any questions about that? Okay, on to the next question then. So there we were given the growth equation. In this next one, we have to develop it. I might do this one and then come see the individual right? Okay. A pile of sand initially has 5,000 kilograms, but it decreases at a rate of 12% per year. So, from here, we need to develop an equation. Okay, so we've got the pile of sand, and we're going to use this information here. P0 is the initial population, okay? So the initial mass for us is 5,000. Now we can use P if you want for the population of sand. I might use M. M for mass of sand with regards to time. Now the initial mass is 5,000, right? P0, M0 is 5,000. And then we have 1 plus or minus R. 1 plus or minus R. Now we're told it decreases. So that means it's going to be 1 take away the rate. Now the rate is a percentage, all right? It's 12%, and we must express that as a decimal. Rate R is the rate of growth and decay expressed as a decimal. So that's just divided by 100, right? 12% out of 100%, and then it's to the power of t. So I'll process this a bit. Okay, so because we have decay, we're subtracting the rate. If we have growth, we're going to add it. All right? So we don't have exponential growth here. In this circumstance, we have exponential decay. Find the equation. There it is there. That describes the equation. So it's a pile of sand, right? And so the wind's coming along, the wind is blowing, and this pile's getting smaller and smaller as the wind blows more and more sand away. All right. Everyone okay with that? On to B. How heavy will the pile of sand be after 9 years? So when time is 9, what is the mass of this pile of sand? It's going to be 5,000 times 0.88 to the power of 9. Okay, so we can get that from putting that into our calculator, or if we have the graph, we can trace along it and so forth. So, 1,582.3. Okay, what is the percentage decrease after 9 years? So we've got a formula there for calculating percentage increase or decrease. New amount, take old amount, divided by old amount. Okay, so that was part B. Here we're on to part C. Percentage decrease. New, take, let's write that properly. New, take old divided by old. So our new amount is 1582. Take away the old amount is 5,000. And then divide that by the old amount. Okay, that's going to be a decimal, and we multiply it by 100 to convert it to a percentage. So 1582 6.6836, 68.36% decrease. Yeah, so this is a formula to calculate the percentage decrease or increase. So in your notes book, it's just here. So we have the new amount, take away the old amount. So the new mass, okay, after 9 years, the mass is 1582. Take away the initial mass, divided by the initial. That's going to be how much it's changed. It's changed by 68% in the 9 years. Yeah, is that all right? Yeah. Okay. And the very last one, how long does it take for the pile of sand to halve, for its mass to halve? Okay, well, look at this. This is the equation of the pile of sand, okay? And we want to know how long it takes for the mass to halve. Well, its initial mass was 5,000, so when it halves, it's going to be 2,500. And so we're trying to solve this equation. 5,000 times 0.88 to the power of t equals 2,500. Okay, so we're saying, what's the time value that makes that true? All right, we'll do this from our calculator. We'll sketch the equation here. Y equals 5,000 times 0.88 to the power of t. We need to set up our V window. Y max. All right, we don't consider negative values of time. So we're going to go from x min is 0, x max. Now look, I know from what I've done here, I know after 9 months, the mass is already past halfway. All right, so that means for my calculation here, I don't need to consider a V window further than 9. So I can put my x max as 10. The lowest the mass could possibly be is 0, and the highest it is 5,000. So with those constraints, we're ready to sketch it. So 5,000 times 0.88 to the power of x. Oops, I did divide. Set our V window 0 to 10 and 0 to 5,000. And so you can see we've got that beautiful decay equation. And we're interested in this, right? We're interested in the x value when the y value is 2,500. So we're doing an x calc. When y is 2,500, the x value is 5.42. So after 5.42 years, the wind has come along and blown half the sand away. We go. All right, so the way we're doing these calculations, right, this isn't the most efficient way to perform these calculations. We can use equation solver, but the reason I would like you to practice this way is it gets you to think about the V window in the context of the problem, which is a very, very important skill. And so it allows us to do that 12H exercise at the same time as we're doing I1 and I2. So these ones will start relatively easy. They are ones you're encouraged to use your calculator on, get the graphs up, get the V windows sketched appropriately. So there we go. So let's make a start with exercise 12I.1. That's where we'll dedicate our efforts today.